All right, thank you so much, Saba, for highlighting the importance of robustness and metric evaluation. From vision language, now bouncing back to LLMs, I would like to introduce our next speaker, Sarath Chandar, who's an assistant professor at the Department of Computer and Software Engineering at Polytechnique, a core MILA faculty member, and also an adjunct professor at the Department of Computer Science and Operations at University of Montreal. He also heads the Chandar Research Lab at Polytechnique, which focuses on several areas of machine learning, including deep learning, reinforcement learning, lifelong learning, and NLP. So without further ado, he's going to share with us today his research insights on the frontiers and challenges of LLMs. Go ahead, Sarah.
Thank you. Thank you for the introduction. Okay. I have 25 minutes. It's a lot of projects to show in 25 minutes. So I'll get started directly. Today I'll be talking about large language models, but I'm sure you have heard about large language models like everywhere, and even in this symposium, through other speakers, right? But my talk is mainly going to focus on some of the challenges that exist in deploying these large language models for downstream tasks and how we can overcome them, right? So we're not going to solve all the challenges, but the goal is really to show you some existing challenges and how to overcome them. If at all you care about using large language models in your applications. Okay, but before I get started, a very quick 30-second overview of what we do in my lab. We work on three major research areas like deep learning, reinforcement learning, and natural language processing. My long-term vision is to develop interactive learning algorithms that continually learn from experiences. Okay, so when I say interactive learning algorithms, so this includes methods like reinforcement learning, natural language processing, and even sequential models, which are the core machinery behind both RL and NLP, right? And when I talk about continually learning systems, these are for example, reinforcement learning systems and lifelong learning systems, okay? We do have several projects in the intersection of these areas, but for today's talk, I'll be focusing mainly on some of the efforts in my natural language processing subgroup. Okay, so I don't want to spend too much time motivating language models, but here is one slide, introduction or motivation, which shows that the rate at which these large language models grow is alarming. And now we have models up to 1 trillion parameter, right? So as models get bigger and bigger, you need a lot of data to train. Some of these models are trained with almost the entire web, right? And I need a lot of money, $20 million, $100 million to train some of these big models. A lot of compute, and there is also environmental concerns that you are affecting the climate by producing a lot of consuming a lot of electricity, etc. Right? So there are, of course, there are also ethical challenges and other things, right? So there are a lot of issues. However, the technology is getting adopted very quickly. So there is a lot of applications just in the last few months, which use models like ChatGPT for very, very creative tasks, very difficult tasks, which were previously not possible, right? So in some sense, this is a revolution of dialogue systems. Even though what we used to think as dialogue system 5 years back is very different from models like ChatGPT. So in this talk, I would like to talk about, as I mentioned before, I would like to talk about mainly the issues, some of the challenges in applying these large language models for the tasks that you care about. Okay, so here is a list of questions that we will focus on. I don't want to read the list and spend a minute, so I'm going to go through these questions one by one. Okay, so the first project that I would like to talk about is, can we use these large language models as differentiable knowledge bases? Okay, so what do I mean by that? So typically, you train a language model using lots and lots of data, sometimes entire Wikipedia, entire web crawl, etc. Right? So in some sense, they are encoding these knowledge that exists in Wikipedia and the entire web in their parameters. Right? So then the natural question to ask is, can we treat these language models as knowledge bases? and retrieve the information that we want to retrieve from them directly, instead of using the traditional knowledge graphs or knowledge bases, right? Like so this was a work done in 2021. Okay, so it's ACL 2021, which means it was done in 2020, which is very old for today's standard. Okay, so however, the reason why I would like to showcase this work is because this is probably the first work which showed that you can actually take this parametric knowledge in these large language models to do, for example, tasks like knowledge graph completion. Okay, so here we specifically focus on link prediction, okay, by adapting masked language models, okay. I will not for this project, but for most of the projects that I'm going to show today, like I'm not going to get into the technical details of the model or the training. You can read about them in the papers, and you can also talk to me after the talk. Okay, so but I just want to give you an overview of like what this MLMLM is doing. So the basic idea here is really to take any pre-trained language model, okay, and somehow convert this model into a lookup table, like where you feed in questions like part of like a knowledge triple, like for example, Obama was born in dash, right? Like so I want to know where he was born in. Okay, now I can feed this triple with missing entity to this knowledge graph, okay? And we created a ranking system, which at the same time considered millions of tokens that are possible and ranked them accordingly to tell you like what would be the most probable answer, okay? And at that time, like we showed that you can achieve state-of-the-art performance in completing knowledge bases when compared to traditional methods that people were using for completing knowledge bases, which did not use large language models. Okay, and what is interesting is like it comes with a more efficient inference procedure in the sense KGBERT, which was the previous method to use BERT for completing knowledge graphs, like it takes a lot of time, like as the number of entities increases, because it is really a naive way where you feed each triple, like Obama was born in, you feed every possible token and see how much probability the sentence has, right? Like so, as the number of entities increases, you're going to do more forward computations. On the other hand, like MLMLM can do this in one shot, like where you just do one forward pass and then be able to make prediction about like what would be the country where Obama was born in, right? Like so as you can see here, it really scales well, even with millions of entities that you care about. And what is really interesting is you can also use this method to predict totally unseen entities, like which at the time, like none of the previous methods can really do, okay? So the only comparison that we have is with random baseline and a Roberta model, which was not fine-tuned. And you see that like the ranks for MLMLM are much better. These are entities that the model has never seen before, okay, or not trained on before, okay? So what is interesting here is the fact that even non-fine-tuned Roberta performance is much better than random baseline's performance, okay? So this kind of verifies the hypothesis that these models do hold some knowledge in their parameters, right? Like, so now the question is, how do we make use of this knowledge? Like, so this is one example application where we made use of this knowledge to complete knowledge graphs. And you could think of any other applications where like you can use this knowledge, right? Like now this kind of brings us to the next question that I want to ask. So given that we know that these models do have parametric knowledge of the world, now like a more practical question is, do they use their knowledge effectively, right? Like, so let's say I train my model with lots and lots of data, which means lots and lots of knowledge, right? Like, so there are two questions here. Like, so one, can they pick up all the knowledge that exists in the data? Two, let's say they picked up the knowledge, can they apply this knowledge in new tasks that they're going to see in the future, right? So these are important questions to ask if you really care about deploying these models in downstream applications, okay? So now this is the work that is done by Amin Hussain, a master's student at McGill. So we're just preparing it for submitting to EMNLP, but it is an archive already, so you can read it in detail. The work is about measuring the knowledge acquisition utilization gap in pre-trained language models. Okay, so what we do here is we take any pre-trained language model, like, so it could be like OPT or llama or like GPT, whatever you can think of, right? Now, as a first step, we try to extract as many parametric knowledge from this model as possible. So how do we do that? We take a bunch of knowledge facts, okay, and we try to see if this model has these knowledge facts by doing some sort of soft prompting, okay? Now, once you collect a bunch of knowledge facts that we for sure know that it exists in the model because we collected it from the model, right? Now we're going to create a downstream task, okay? So the downstream task is really simple. The question, for example, where did Barack Obama graduate from? Okay, so now there are a bunch of answers and the model has to pick from these options, okay? So Obama graduated from Harvard, he went to Stanford, okay? There are even irrelevant facts like Bill Gates studied at Harvard, etc. Okay, now first we train a model to solve this particular task that you see here, okay? And then we test it on completely new test set, okay? So now we have carefully set up this process in such a way that we remove all the confounding factors, and the only way in which the model can succeed in this task is by using the parametric knowledge it already has, okay? So a good model, a model which has the ability to use all its parametric knowledge, should be able to get 100% in this task, right? So now let's see what happens if we do this setup with some of the existing language models. So in the left side, you see that there is actually a gap, okay, on how much knowledge these models can acquire from the data itself, okay? So we have, so these are normalized figures, like basically we have some encyclopedic knowledge, and like we show you here that like how much of this knowledge can we retrieve like from the parametric knowledge of BERT, Roberta, GPT Neo, and OPT, like all approximately similar model size, like 125 million, okay, parameters. And you can see some interesting observations here. Like, so BERT seems to acquire more knowledge out of this encyclopedic knowledge base than OPT, right? Like which is a more recent model, right? On the right side, you see how much of this acquired knowledge can be utilized in the task. Okay, so that is the second gap. So that is the acquisition gap. Gap one is the acquisition gap, like how much gap that exists in acquiring the knowledge. Gap two is really the utilization gap, where you see that different models have different gap in utilization. And interestingly, OPT in this case has a little bit more utilization of the knowledge, even though it has less knowledge, okay? So this is interesting. Now, this is a summary figure which shows you that different models have different, are capable of acquiring different amount of knowledge, and they also have different ways of like using this knowledge. Okay, so some models use their knowledge better than other models. So it is important that we keep these in mind, like when we deploy the system. And another side effect of like this project is like now we can think about how can we explicitly train these models to acquire knowledge and also to better utilize these knowledge, right? Like, so which is mostly the future work that we will be working on. Now we also have more interesting results in the paper. Like, so one of the results is this, like where we show that this utilization of knowledge actually gets worse when you go for downstream tasks which are out of distribution. Okay, so the way in which we simulate that here is by using completely unseen relation types as our like validation set. Okay, and we see how these models perform in utilizing knowledge for these completely unseen relation types, right? Like, as you can see, their performance drops very quickly when it is out of distribution, which means that the more diverse tasks that you're going to use these models for, like, so there is going to be some loss in knowledge or utilization of the knowledge. So you cannot see similar benefits in every application. Okay, so like in some sense, the type of application matters, like depending on what data you use to train these models. And like a more natural question to ask is, can I just scale my model? Will this gap get closed, right? Like, so we show for OPT in this case, like starting from 125 million to 13 billion. So you can see here that the amount of knowledge that is acquired increases, okay, as you scale, which is intuitive, right? However, the gap that you see in the acquisition versus utilization, right, that still persist. Okay, in some sense, the scale is not going to solve this problem of like how to use the knowledge that you already have, right? Like so this is same numbers in a different way of explaining things. Like so, where we show that the amount of like basically gap one, right? Like it reduces over time, like sorry, over scale, right? However, gap two still persists, or sometimes it gets worse too, right? So it's like the most important question based on like which is the output of this paper or project is like, how do we close this gap? Like, so how do we make sure that these models utilize their knowledge very well? Because we do spend a lot of money on training these models. Like, so they better use all the knowledge from these training data, right? Okay, so now building on top of this, right? Like, so I talked about using the knowledge. Like now the next question is like, what kind of tasks I can use this knowledge, right? Like, so, or more broadly, can we use these models as task solvers? Okay, like, so can I just take a pre-trained GPT model and do whatever task I want to do and continue doing this, right? Like, so this is like a work done by my intern Sanket with my PhD student Darshan. Like, so this was done long back, but it is still under review at JMLR, where the process is so long. Okay, so but it is almost there to be accepted. But the paper is out in archive. It's a long 30-page paper which investigates the role of pre-training in lifelong learning, both for language and vision tasks. Okay, but for the purpose of this talk, I would just focus on the language tasks. So now the question here is, does pre-training, which is typically done in these large language models, help in alleviating forgetting that happens when you put these model in deployment and continually learn several tasks, right? Like, so like a very interesting initial observation is like, I don't do anything between these blue line and red line. Okay, these are like, this is the same model learning 5 different tasks sequentially. Okay, the only change is instead of using random initialization for red, I'm using pre-trained initialization, which is the blue. Okay, and you can see here that there is almost no forgetting when I use a pre-trained model versus starting with a completely random model, right? So this raises a question. Okay, so is it a good idea to always pre-train, like take one of the OPT models and then start solving your task, like if you want to do things like lifelong learning, right? Like, so now, how do different pre-trained initializations affect forgetting? Okay, to study this, we took like different language models like Distilbert, BERT-based, RoBERTa-based, BERT-large, etc. And like we tried it with 5 different data sets in NLP. Okay, and you can see here that larger models typically undergo less forgetting. Okay, also what is interesting is RoBERTa-base has similar performance as BERT-large. Okay, which means the diversity of the training data matters a lot. Okay, like when it comes to like not forget the previous task and make use of these knowledge, right? Now to stress test this further, like, so we introduced this 15 diverse NLP task challenge. Okay, so where we take a pre-trained model and train it on 15 different tasks sequentially. Okay, and we basically show that once you start looking at diverse set of tasks and you want to do all of them together, which could be treated as a multitask learning problem or lifelong learning problem. Okay, so that is where the problem arises. These models like deteriorate very quickly. Okay, so like, so they have bad performance, or they forget more, or the accuracy drops like when you have to do diverse set of tasks. Okay, which means even now, like taking these model and fine-tuning on just one task and using the fine-tuned model is the best approach. Okay, so the moment you start reusing the model for multiple tasks, which is ideal if you want to serve a 180 billion parameter model, right? Like you don't want to put multiple copies of 180 billion models like in different servers, right? Like but however, that is still a problem which needs further exploration. Okay, and in the paper, like we also show like in terms of optimization, there is a benefit in starting with pre-trained models, because pre-trained models typically put you in a wider minima space, like, or a flatter, much more flatter region, where it is possible for you to learn many tasks simultaneously or sequentially, which is typically not possible when you have like a random initialization. Okay. Okay, so I know I have 5 minutes. I will quickly go through like 2 more projects. And now like I will shift my focus to explainability, like and debiasing of these large language models. Okay, so first I want to talk about explainability. Okay, so this is like a project by my PhD student Andreas. Like, so this is also in preparation for EMNLP, but this one is not in archive due to anonymity policies. So the project is faithfulness measurable language models. Okay, so here this is based on like a very fundamental question, which is a lot of us care about explainability of these language models, right? Like, so one application that I can give is like use a language model for ranking resumes, let's say. Okay. Now, if there are any inherent biases in your data, now this is going to show up in your like classification algorithm, and it is a problem, right? So like a very famous example is Amazon ditching a recruiting tool that favored men for technical jobs. Okay. Now, even if you have really good model, okay, which has no bias, we should remember that nothing prevents humans from filtering according to their bias, right? So I give you a perfect model to use. You as a recruiter can still decide to bypass the model and bring in your own biases, right? Like, so this is where explainability is helpful. If at all the model is also explainable, okay, then it can say that, oh, this particular decision is based on these biases. Now maybe you should rethink like how you made this decision, right? So now like explanation is not going to solve the bias issue, right? Like, but it can lead to some discovery and change. So that is a hope here. And even the GDPR Article 13 says that we should, like any decision-making system that is using AI should have some explanation capabilities so that the decision makers, like the humans, make more informed decisions, right? Now, I'm not going to get into the technical details of how we solve this issue, okay? But the major premise of this work is that there is a lot of work in the literature on coming up with explanations for large language models, okay? However, even these convincing explanations can still be wrong, okay? So how do we know what does a correct explanation look like? It is almost impossible to tell what does the correct explanation look like, okay? So this is where the question of faithfulness of these metrics come into picture, okay? So there is a lot of work on faithful explanations of language models, okay? However, most of them have some limitations, like either they're speculative, they're computationally expensive, limited in scope, or they don't consider the deployment setting, etc. Okay? What we show here is like possibly the first attempt to come up with more faithful explanation of language models, which kind of exploits the fact that we are using masked language models. Okay, so what we are going to do here is, okay, so I will finish in 2 minutes. So what we are really trying to do here is to train the model in such a way that it learns to use masks properly. Okay, so instead of just using masks as a training objective, like we try to bring in the masks within the distribution of the training data, so that when I mask the most important word, the model can change its prediction, right? Like which is not possible if the mask is out of distribution. Okay, so the main contribution here is really to make sure that sorry, I'll directly go to the result. The main contribution here is really to make sure that like we fine-tune the masked language model in such a way that its explanations become more faithful. Okay, so here you see the comparison of what happens when there is no masking, when you do complete mask, just masking based training, or do 50-50, which is basically do some part of masking, some part of no masking, right? Like, so like in the left side, you see 100% masked performance. When I mask all the tokens, I want the model to predict majority baseline, which is the black line. Okay, and you see that vanilla language models, which are the red color, they do worse than majority baseline, which means mask is not within the distribution of this language model. Okay, we kind of fix that issue with green, which is an ideal scenario to be in. Okay, so in some sense, like we propose a new way of training these language models, which makes sure that these models are inherently explainable, like when we use these masks to come up with explanations, right? So now this project was more about like understanding how the model makes the decision, like so, and coming up with explanations. Let's say we come up with explanations, and it shows that there is some bias. Okay, now how do I remove this bias, right? Like so, this is where debiasing comes into the picture. Like this is a work done by my PhD student Abdul, like who's here today. Like so this is also in preparation for EMNLP, but it is in archive. The work is should be attend more or less like modulating attention for fairness. Okay, so in the literature, first of all, like there are hundreds of work on how to avoid biases. Like there are work which looks at pre-processing the data set or changing the training objective or doing some post-processing after training, etc. Right now, what we propose is a really, really simple way to remove bias in these large language models, which is based on the fact that most of these models are transformer models, which means there's an attention layer followed by an MLP, right? Now, what happens at the attention layer? Okay, so when the attention layer, let's say this is my attention, if I try to widen the context of this attention, then it might reduce the significance of the word she, right? Similarly, like sometimes it might be the case that the model is not focusing on he, but you attempt to play with the attention, then it is going to start looking at he, right? So an ideal situation is like if I have a knob to modulate the attention in such a way that the model attends less to biased words, right? Like so that is what we aim to do. Like so, the way in which we are doing this, I'll skip the details. So the way in which we are doing this is like, so we have a separate validation set, like which can be used to tune the attention, like attention modulation, okay? And here is an example, like where we show that for both BERT and Roberta, like the right amount of modulation is not in the left extreme, not in the right extreme, okay? So it's somewhere in between. And we figured this out by using the validation set, okay? Now the process is really simple because you have a trained model, you just tune the attention. That's it, right? Now, like we compare this with various other intra-processing methods that exist in the literature. Like so EAT, which is our method, as you can see here, has better demographic parity, okay? At the same time, the loss in accuracy is minimal when compared to the second best model, which is random perturbation, okay? And this also like works well when I combine this method with other bias mitigation methods. So here is a graph which shows EAT does better in terms of removing biases with respect to age, gender, sexual orientation, disability, etc. Right? So most of these results are based on classification tasks. We also have details about how to use this in generative tasks in the paper, but just to give you like an example of how that would look like, right? Like so, the United Nation of Islam is an African American dash. So here are the results of the vanilla model, random perturbation model, which is the previous state of the art, and EAT. Okay, so as you can see, EAT is less biased. And here is another example where we're talking about a film actress, while the first two models are being more sexist, like the third model, like which is our model, is giving some reasonable answers. Okay, so I will stop here with just one final slide, which is like there are even more challenges to like when we talk about large language models. Like we are working on some of them. Like please come talk to me after, like during the 5 to 7. Like so, for example, how do we make sure that these models produce factually grounded answers? Make sure that they don't hallucinate, right? Like so, how can we add memory to these models so that we can, for example, create a digital assistant which maintains the profile of the user over time and learn their preferences, etc. Right? Like so, and in general, how do we use these models to solve tasks that we care about? We also do a lot of work in optimization, which I did not talk today. Like, so how do we efficiently pre-train these models? Like, for example, accelerating the training 2x is going to save $10 million in training GPT. Okay, so how do I do such acceleration? And how do we design updatable language models where I can update the knowledge every day based on the news events that happen over time, right? Because I don't want to retrain a 20 million model like again and again. And finally, how to handle multiple modalities. I think I should have talked about combining vision and language, but you can combine vision, language, audio, like other sensors, etc. Right? So I will stop here. I just want to also make a quick announcement that there's going to be like the second edition of Lifelong Learning Conference happening in Montreal today. So like in Montreal in August. So if you care about topics like lifelong learning, meta learning, multitask learning, transfer, which are basically the future of machine learning. Okay, so like you should consider attending the conference August 22 to 25. Okay, it's going to be happening at McGill in Montreal. Okay, I know I was a little bit late, but I'll stop here. You might not have time for questions, but you can, maybe one question, yeah. Any question? No question?
Because mine are still racing.
Okay, it was a sprint. Okay, but I'm going to be here at 5, so you can please come talk to me if you're interested in any of these projects. Thank you.
Thanks so much, Sarath.